Hello and welcome to our discussion of Chapter 4. We're going to briefly start talking about molecules and compounds today. We'll dive into how do atoms that we so in-depth looked at in Chapter 2 and 3 with their electron clouds, how do those atoms now take those electrons and react them into different types of bonding? So how do molecules come about and how do compounds come about? The first thing that we kind of want to explain is how are elements different than molecules, and how are they different from what we see on the periodic table and what we've spent so much time discussing in previous chapters. When elements react and form a compound, they are completely new substances. I love this example with hydrogen, oxygen, and water. When we think about the reaction between hydrogen, which is a diatomic gas, oxygen, which is a diatomic gas, meaning diatomic, two atoms are always found bound in nature together. And what they form is H2O. We'll take a minute and balance those. Now, what we see in this reaction is the idea that we have two elements that are going to be joined together to form this new molecule. And what's interesting is that the reactants, even though they are composed of the same thing for the products, they are completely different substances. Namely, hydrogen is an explosive gas. Oxygen is necessary for combustion reactions, so you can think of it as being reactive in explosion reactions. And then there's water, which is used to put out fires. They're, yes, composed of the same atoms. They might be balanced so that we are thinking about the same number of atoms are here, same number of electrons. But when two or more elements combine, they form an entirely new substance. We see this with sodium and chlorine as well. Sodium is an explosive metal. Chlorine is a poisonous gas, yet somehow when they come together to form sodium chloride, we eat it every day on our food. That's table salt. And so what we're gonna investigate today in this chapter is this idea that how did the elements we just studied come together to form new molecules or new compounds. And we'll be able to dive into those definitions a little bit more, see their reactivity in elements, and see what are new properties of the products that they form. I want to start here with the two main types of chemical bonds, ionic versus covalent. There's a couple of new things out there that talks about metallic bonds. We won't be talking about metallic bonds in this class. Very interesting new way of thinking about how metals bond with other metals, but we're going to fixate on the two main types that are prevalent in most general chemistry textbooks. Ionic bonds and covalent bonds. Now, an ionic bond is going to be between a metal and a nonmetal. A covalent bond will be between two nonmetals. So there's going to be this big difference between how elements react dependent on their physical properties, namely the periodic trends that we just looked at. We'll dive into that in just a second. Let's just answer this question. What is a chemical bond? Now, a chemical bond is going to be defined as a force that holds atoms together. We've been talking about Coulomb's law a lot so far, attraction between electrons and protons. Opposites attract. That is defining our idea that protons are attracted to electrons, and that's a good thing. We like that. That is usually when we see energy lowering, meaning it becomes stable, whether we're talking about an electron, whether we're talking about a molecule. If we have a lot of attractive forces, those attractive forces mean energy is being released. It's exothermic. We'll look at Coulomb's law again and be able to plug in some values here. But when we think conceptually about Coulomb's law, opposites attract because overall the energy is lowering for the system. The system is becoming more stable. Like charges repel. These are things like 2 protons or 2 electrons. This is a sad day for us. We don't like being repelled. It's energy raising. And this literally means unstable or reactive. So once we start thinking about the force that holds the atoms together, when 2 atoms come together, hopefully their attractive forces are going to outweigh their repulsive forces. And that's what we're going to start to look at. Chemical bonds form because overall, they lower the potential energy of the atoms. We want the attraction to be greater than the repulsion. This would be the idea of potential energy overall decreases when bonds are formed. So what we see in nature is that forming bonds releases energy. The reason why is because the attraction between those 2 atoms, specifically the protons of one and the electrons of the other, those attractive forces releases energy to the surroundings. Forming bonds releases energy, which means the opposite for breaking bonds. Breaking bonds requires energy. We can think about forming bonds as exothermic, breaking bonds is endothermic when we talked about energy way back in Unit 1. So understanding this, what does this mean for 2 atoms? Well, let's just say that I had atom A over here. Here's his nucleus. He's got some positively charged things, and he has an electron in an outer orbital. We'll call this atom 1. On the other side, we'll have atom 2 with some protons in its nucleus and an electron in its outer orbital. Now, when these 2 atoms want to bond, one thing they have to keep in mind is that opposites attract. There's some attraction between one atom's protons in the nucleus and the other atom's electrons, and the same over here, attraction. These are the good things. These are what actually holds the atoms together. Now, what we do have to remember, though, is that electrons repel and protons repel. So there has to be a balance. There's going to be a balance between all of our atoms when they start to bond. They are trying to overall have their attractions more favorable than their repulsions. If in nature we do not see these bonds form, it's because they're not attracted to each other enough. Those bonds aren't forming because they don't have anything to put them together. if we do see a bond in nature, like water, water bonds to two hydrogens. Here is a covalent bond. How I know it's covalent is because oxygen is a nonmetal and hydrogen is a nonmetal. Now we'll decide what covalent means in beyond just the identity of the two atoms bound together, but that bond forms because it is energy releasing. The attraction between the hydrogen and the oxygen is greater than the repulsion between those two atoms. So there's something favorable holding those two elements together. And that's what we're going to investigate. For a definition, an ionic bond, beyond what we said, a metal and a nonmetal, electrons are going to be transferred. Now, specifically from the metal to the nonmetal. Why? For reasons that we just talked about. Metals have very low ionization energies. Nonmetals have very high negative electron affinities. So when we look at an ionic bond, we will see ions are formed. Why ions are formed is because of this periodic trend. Metals have a very low Z effective, and so it's very easy to take a metal to a metal plus one cation. Nonmetals have a very high Z effective, so they want to gain more electrons. So the nonmetal can go to become an anion very easily. So there's this transfer of electrons from the metal to the nonmetal. Metals give them up, nonmetals take them in. And so it's really an electrostatic attraction. That holds our ions together. Why we call it an electrostatic attraction is because we have opposites. We have a cation plus an anion forming that bond. And those opposite charges are going to attract. That's Coulomb's law. Opposites will pull together and they will be composed in this solid state of opposite charges. I'm just using pluses and minuses to identify the cation and the anion. Notice that these are alternating. What happens here is this is what we call a lattice structure. Think about when you plant a vine, if any of you had ever seen a vine growing along a wall or growing in a backyard, when you have a lattice behind it. Lattice is usually a structure that allows things to build up or to grow alongside. This alternating plus and minus creates the attraction between the cations and the anions that allows it to build up into what we know as a sample of an ionic compound. So in a solid state, when we have something like sodium and chlorine coming together to be sodium chloride solid, we have some sodiums. Sodium is the metal, so we know it's going to be the cation. We have some chlorines. He's the nonmetal, so he's going to be the anion. So this alternating sodium plus one, Cl minus one, builds up all of our alternating charges so that we can truly see, yes, there's one sodium and chlorine ion here that is represented with NaCl. What we call that is a formula unit. A formula unit will be the smallest whole number ratio of ions. So when I think about a sodium +1 and a chlorine -1, yes, they make sodium chloride. There is my formula. It's going to be called a formula unit because in reality, it's not just one cation and one anion. It's a lattice of a huge amount of cations and anions, right? It's this buildup. And we'll talk about lattice energy in just a little bit. We'll focus our discussion first on ionic bonds, and then we'll move into covalence. But I just want to get a definition of covalent bond before we continue. For a covalent bond, we have a little bit different picture. A covalent bond is going to be a sharing of 2 electrons. Specifically, it could be 2 or more, but we'll stick with 2, occurring between, specifically, 2 nonmetals. And I'll say here 2 electrons or more, but at least 2 in order to get that bond to occur. Now, why is this different? Why are we sharing instead of transferring? With 2 nonmetals, we have a very high ionization energy and a very high negative electron affinity. So these 2 nonmetals don't want to give up their electrons entirely, but they will share them in order to reach a stability. Now, if we kind of look back at that formula unit right there with sodium +1 and chlorine -1, we can hint to why there's a stability. We saw that there was a stability in forming specific ions because of reaching noble gas configuration. We talked about that a lot. So now the only difference between an ionic compound and just the formation of the ion stability is just bringing them together in the lattice. For a covalent compound, we do not see ions. There's going to be a stability in sharing electrons. We will share electrons to reach the noble gas configuration. So, the sharing occurs between the 2 nuclei, and it will be a very structured look. So if we think about hydrogens and oxygens in water, oxygen has an electron configuration of helium 2s2, 2p4. We see that in its outermost shell, we need 2 more electrons. So oxygen tends to make 2 bonds. Now it can make more, it can make less, but in general, why we see in water, we needed 2 bonds to make that molecule is because oxygen needed 2 more electrons. Once it reaches H2O status, it gains 2 electrons to put in its 2p orbital. So it becomes a 2p6. Same thing with hydrogen. Hydrogen has a 1s1 configuration. We know it needs 1 more electron. So it makes 1 bond. Hydrogen is very special. It only makes one bond and one bond only. The reason for that is because the principal quantum number n equals 1 only has an s orbital, and therefore it only can hold 2 electrons total. So very important to note that once we get into the second row and the third row and beyond, we can start seeing these typical things and atypical things. But hydrogen is very predictable, and hydrogen won't make more than one bond. All right, for a covalent molecule like H2O, this is not called a formula unit. This is called a molecular formula. Why it's called something else is because it's an actual number of atoms in the molecule. And here's where I'm going to define the difference between a molecule and a compound. A molecule will be 2 or more nonmetals so a molecule has to be covalently bonded. A compound will be 2 or more atoms. It can be covalent or ionic. Typically, we save it for ionic compounds, but I'll say ionic or covalent. So it's kind of like everything that has bonds is called a compound. Only things that have covalent bonds are called molecules. Lovely. So here's just a nice representation of what happens to make an ionic compound. I like this picture in your textbook. Again, it shows the idea that we have sodium metal and chlorine gas, which are very, very different. Sodium metal is very shiny. It has to be stored under oil so that it doesn't explode and react with the water or moisture in the air. Chlorine gas is this yellow poisonous gas, very dangerous. But when they come together, when that electron pops off of the sodium and goes boop, 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 all the way over to the chlorine, then all of a sudden it becomes this miraculous thing that makes food taste great and is a good old-fashioned preservative. So looking at reactions where we make bonds, we take species, atoms, elements, whatever you want to call them, we take things and we conform them into something completely different. Here's a summary of the types of chemical formulas that we can see. A structural formula is usually what depicts the most amount of information. It's that visual picture of the compound. For a structural formula, what we see is something like H2O written out like this, where we can see the actual relationship and the bonds. A molecular formula is what we call that covalent compound in its little condensed area here, 2 hydrogens and 1 oxygen, H2O. It tells you the actual number of elemental atoms in the compound. It does not tell you how they are bonded. Notice the 2 H's are condensed there on the left, but it doesn't tell you that each one of those is generally connected to the oxygen. That's the structural formula. And the empirical formula is going to be something new. This is going to convey the simplest whole number ratio of the atoms. So molecular is the actual number. Empirical is the relative number of atoms for a covalent compound. You can also do an empirical formula for an ionic compound, but let's face it, the empirical is the same thing as a formula unit for an ionic compound. Where we see a big difference with molecular formulas and empirical formulas are things like covalent compounds. Specifically, if I thought about H2O. The molecular formula, H2O, there's 2 hydrogens and 1 oxygen. That's the same thing for its empirical formula. But for something like H2O2, there's 2 hydrogens and 2 oxygens. That ratio can be reduced. The empirical formula is HO. This gets into a better idea once we start doing our determination of molecular formulas at the end of this chapter. But let's just choose another one, C8H8. This is a carbon and hydrogen molecule. Carbon and hydrogen are both nonmetals, so we can call it a molecule. In the molecular formula, it's the actual ratio, 8 carbons to 8 hydrogens. For the empirical formula, it would be CH, 1 to 1. Lovely. For, again, molecular formulas for molecular molecules, we have ways of being able to look at those outside of the structural formulas and the molecular formulas and the empirical formulas. Those are all very important. We'll focus on those. When you get into higher levels of chemistry, specifically organic chemistry, you'll have molecular modeling. We'll see a little bit of molecular modeling in the next unit. And it's very, very interesting to see how the actual structure of the atom looks in 3-dimensional space. The ball and stick model is representing atoms as balls. Why we do that is because typically when we think about the smallest shape or the smallest surface area shape, it's a sphere. And that's what we can kind of think about as all of our atoms as little spheres. Typically they're color-coded. There's not any one way to color code. This is just how your book typically color codes. It's not the only way to color code. But normally when we start seeing these ball and stick models, they'll color code the elements in the molecule so that you can see which one is which. For instance, this is a molecular formula, CH4. The structural formula shows all of those bonds. All of the hydrogens are bound with single bonds, one line to the carbon to each hydrogen. The ball and stick model, notice how it starts to look more like a 3D shape. This is where we'll get in chapter 5 and 6. It'll be very exciting. Space filling models are a little bit more accurate representation of what we think molecules might look like. But again, we won't be hanging out with those space filling models. We'll do some ball and stick models. We'll do a lot of structural formulas and definitely a lot of molecular formulas. Now, the theory behind bonding is called Lewis theory. Now, we're going to start with ionic bonding. We'll get to Lewis theory in covalent bonding. It's a little bit more complex. Ionic bonding is what we're going to start with. Now, what this predicts is the number of electrons a metal atom should lose or a non-metal atom should gain in order to attain the stable electron arrangement. We call this the octet rule. What this is going to mirror is that noble gas electron configuration. And we know that there is a completeness in filling our valence electrons. So when we think about what the valence electrons are, the S and the P, remember we have 2 electrons in the S and 6 total in the P. There's the 8 electrons, 8 for oct, 8 electrons. Now that doesn't mean that that's all that the atom can gain or lose, but it is going to just be honing in with those main group elements around the octet rule. Now, using the octet rule, the idea that 8 is our magic number, it allows us to predict the formulas of ionic compounds that result from the combination of one metal and one nonmetal. The relative strengths of those ionic bonds are also based off of Coulomb's law. So something that has a +1 and a -1 charge can be predicted. Sodium did have 1 electron, chlorine had 7. Sodium gave 1 more electron to chlorine. There's your 8 electrons total. we can always look at a +2 and a -2 charge. We're going to do a lot of practice with pulling these guys together. Magnesium is in group 2. It has 2 valence electrons. It will gladly give those 2 valence electrons to oxygen. Oxygen needed 2 more valence electrons to reach its 8 octet. Now, when we think about those 2 compounds, who's stronger? Whose ionic bond is a little bit stronger than the other? Well, think about sodium and chlorine holding hands with 1 hand each. 1 electron was transferred from sodium to chlorine. Magnesium and oxygen have a greater value here in our charges. So we'll revisit Coulomb's law and we'll be able to calculate why magnesium oxide is a stronger bond than sodium chloride. A little bit more about Lewis theory. It implies that the position of the ions in the crystal lattice are critical to the stability of the structure. We will see how it's not just the electrons transferred. Yes, the electrons are going to transfer, but another important part is building up that lattice. We'll see why that's so important when we start looking at real life calculations and what we've observed in the lab. It also predicts that moving ions out of the position should be difficult. Ionic solids should be very hard. Once they build that lattice, it's a very dense structure. And so, yes, we can react them, but breaking up an actual ionic compound just with hands or with a hammer is something that's slightly difficult. Ionic solids tend to be hard compared to molecular solids, things like water. A lot of molecules could be gases or liquids. Not a lot of molecules are hard solids. Lewis theory also implies that if the ions are displaced from their position in the crystal lattice, repulsive forces should occur. So we'll start to see why that lattice is so important to us. And it predicts that the crystal will be unstable and break apart if the ionic solid does, or the lattice structure does move or get displaced. And so ionic solids could be brittle. They're hard, but when they are struck with a big force, they tend to just all shatter apart. It also implies that in the ionic solid, the ions are locked in a position and can't move around. It predicts that ionic solids should not conduct electricity, even though there was a transfer and ions are formed. When those ions are stuck in the crystal lattice, that cannot conduct electricity. We can use an ionic solid with water to conduct electricity. However, we can't just put a light bulb in sodium chloride and expect something to happen. And when in the liquid state or when dissolved in water, the ions have the ability to move around. We'll talk about what that looks like a little bit later. And it predicts that's when the ions are free-flowing and can actually conduct electricity. Very interesting. Now, I want to get into Lewis dots. Lewis theory was developed by an American chemist, woohoo, go America, an American chemist in the late 1920s, early 1930s, in order to simplify. Typical American, right? Not only a chemist who wants to make things easy, but an American chemist who wants to simplify quantum mechanics. And so what he uses is this idea that valence electrons can be represented as dots. Because he said, look, we know from quantum mechanics that only the valence electrons, the outermost electrons, go into reactions. And so if I take something like hydrogen, if I just put a little dot there, there's one electron. There's the valence electron. Let's keep going, right? We have helium. Helium has 2 electrons. When we put them together in helium, it's because those 2 electrons are in the 1s2 orbital. They're a duet. They're complete. Drop down to lithium. There's its 1 valence electron. Now, beryllium doesn't have a duet, he's got 2 electrons freely on either side. Boron, 1, 2, 3 electrons. Carbon, 1, 2, 3, 4 electrons. We're again moving just across that second row of the periodic table. 1, 2, 3, 4, 5 for nitrogen. 1, 2, 3, 4, 5, 6. Notice we're just doing a merry-go-round around those elements. The reason for this is to be able to describe how many valence electrons, and Lewis brilliantly came up with this idea to say, how many bonds do these elements tend to make? Well, lithium has 1 electron, so it will give up 1 electron to become lithium plus 1. Beryllium has 2 electrons. He'll give those up to become beryllium plus 2. Boron is a metalloid. He can either make 3 bonds, like covalent, or become boron plus 3. Now, as we continue looking at all of these, what's important to note is that Lewis simplified these Lewis dot atoms in order to quickly identify a typical bonding pattern. So once we get to carbon, why there are 4 dots but 1 on each side is to understand what was typical for carbon. Carbon typically makes 4 bonds. Now that could be ionic, or it could be covalent now, right? So we could see that carbon could have a +4 or a -4 charge, excuse me, it's a nonmetal, but we don't often see that. What we start to see now as we merge over into the nonmetals is both the ionic and covalent bonding definitions could be satisfied. Now, we know the octet rule is a thing. So what we're also aiming for is how many electrons, as we merge over into this nonmetal category, how many electrons does the atom actually need to reach its octet? So not so much looking at the valence count, but 8 minus the valence count. So for nitrogen, he has 5 valence electrons, and what we see is there's 3 unpaired electrons there, 3 extra spots in order to make 3 bonds. We can also think about N-3 for the ion. Again, I'm only picking out the spots where there's an unpaired electron. We know electrons are paired in their orbital diagrams. And so when we're looking at these Lewis dot atoms, they're a simplistic way of truly getting to the heart of what quantum mechanics is telling us. 2 electron spaces for oxygen, so he typically makes 2 bonds, or we'll see oxygen -2. And there's 1 electron spot for fluorine, so 1 bond, or F-1. So a lot of different things with these. What we want to be able to identify is looking at these Lewis dot atoms as a simplistic way of understanding bonding, whether it be ionic or covalent. We're going to start with some of the basic ideas. Overall, atoms will transfer or share electrons to gain an octet. As we have seen in a couple of reactions so far, some elements are not by themselves out in nature. We have what we call a diatomic element. What this diatomic element literally means is that there are 2 atoms covalently bonded. So things like hydrogen, we can think about two Lewis dot atoms. Hydrogen will actually come together with another hydrogen atom in order to make hydrogen diatomic. Notice that this new covalent bond is two electrons being shared. What that does for hydrogen is it creates a duet for each of them. We can also think about writing it this way, with the two dots in the middle. Notice for a covalent bond that the bond is physical, it's direct. For an ionic bond, we talked about the lattice. Let's just look at another one. We'll do chlorine diatomic. Chlorine has 7 valence electrons, so we count up our Lewis dot atoms accordingly. Again, what we see is that these two can be shared so that we make a bond between the two chlorine atoms. Now, a couple of things that we'll talk about once we get into bigger structures of covalent atoms. This is, again, 2 electrons being shared. These guys on the outside are what we call non-bonding electrons. They do not need to bond because they are already paired up in the valence shell. That's something that's understood with Lewis structures. We can also call them lone pair electrons. Now, all of the diatomics that we'll see have this bonding in nature. Oxygen is another one. I want to bring up oxygen because he's a little bit different than the other two we just saw. Oxygen likes to make 2 bonds, and we can see that occurring. Now, when that happens, oxygen literally puts 4 electrons in between those 2 nuclei. This is what we would call a double bond. That is when 4 electrons total are shared. Before, with hydrogen diatomic and chlorine diatomic, 2 electrons being shared is just a single bond. Double bonds, we'll talk about what they are in terms of physical properties and how those double bonds come to existence in later units. But we should note that if 2 electrons are holding atoms together, that 4 electrons holding 2 atoms together is stronger. Just like we talked about with the lattice structure of ionic compounds, the stronger the charge, the stronger the bond. The more bonds in a covalent pair, the stronger the bond. So a single is the weakest bond, a double is stronger. Nitrogen diatomic is another one we can talk about. And nitrogen needs 3 electrons to complete its octet. So you guessed it, triple bond. The triple bond is even stronger. 2 electrons in each of those bonds, which means a total of 6 electrons shared. Now, list of diatomic that we should know. H2, N2, O2, and then all of the halogens, F2, Cl2, Br2, and I2. You should know these. anytime an element of oxygen reacts in nature, it will be oxygen diatomic. Same thing with all of these others listed. These 7 elements are not found by themselves in nature. They are found coupled, diatomic, 2 on that subscript to identify the 2 that are being held together. One last introduction to our Lewis structures would be with ionic compounds and Lewis dots. For an ionic compound, we get a little bit different of an approach. So I wanted to draw out a metal and a non-metal for us so that we can see the differences here. Now I'm just going to pop that electron over, 1 electron being transferred. That makes lithium +1 and chlorine with 8 electrons around it and a -1. Lithium chloride, there's the formula unit. I could see that 1-to-1 ratio, 1 electron, 1 electron. We'll call that extra or valence for the lithium, and we'll call that needed or empty for the chlorine. Now, it doesn't always have to be a 1-to-1 ratio. Sodium and sulfur can react. But see, what happens here is sodium can donate 1 electron, but we still have this empty space for sodium, another sodium to fill up right here for sulfur. So there are effectively 2 sodium +1 cations for every 1 sulfur anion. So the formula unit Na2S. Notice that that subscript identifies 2 sodiums for every 1 sulfur. We can understand that one right there. Now, speaking of ionic compounds, what we want to be able to look at is a little bit more than what Lewis has to offer. Namely, what we want to be able to focus on is a crystal lattice. That lattice is important for us because what we actually end up seeing is that an ionic bond is not just a transfer of energy. If we think about sodium and chlorine coming together, what needs to happen for sodium and chlorine to come together is this. Sodium solid and 1 chlorine, notice there's that diatomic. We'll just take half of it to make NaCl. What scientists thought way back in the day was that all it took was that transfer of electrons. So sodium becomes sodium +1, and we lose that electron. Chlorine gains that 1 electron to become chlorine -1. But that's not the only thing that happens. Lattice also happens. It's the buildup of the actual ions, this idea that tells us the overall energy change for making an ionic compound. Now let's just break this down a little bit and revisit Coulomb's law. If I know sodium will become sodium +1 and release 1 electron, That is called ionization energy, and I can look that value up on a table. It costs 496 kilojoules per mole to remove an electron from sodium. Yes, it's favorable, but it still costs money to pull that, or costs energy to pull that electron away from the nucleus because opposites attract. For chlorine to gain that one electron and become chlorine minus one, that is electron affinity. That releases 349 kilojoules per mole. So overall, if I were just to add those two together, I would see that to make sodium chloride, it would be overall positive in energy, meaning that it costs us. That is an endothermic reaction. But what we actually see is that that's not the case at all. When we go in the lab and investigate this reaction, we can measure the amount of energy change total. That's what we call the overall delta E. The overall change, we'll use delta H because this is heat energy only. The overall delta H energy change is a negative value, and it's a huge negative value. What the heck? Why is this? This is what was puzzling. Doesn't match up. So scientists were really concerned. What is the overall ionic bond? That's the driving force to make the ionic bond, because it's not the transfer of electrons. Yes, the transfer of electrons is beneficial because we have achieved noble gas configuration, but that doesn't tell us why the compound actually stays stuck together so well. What we actually have to consider is the lattice energy. The lattice energy step. When sodium plus 1 and chlorine minus 1 actually come together in the buildup, that delta H is a huge value, and that is the overall driving force for this reaction to take place. We consider, yes, that we need the idea of the electrons actually being transferred, but in reality, that lattice energy step is very, very important. It's the overall driving force to get the reaction to take place. So, a couple of things with lattice energy. Lattice energy is going to be defined as the energy released during the formation of a crystalline lattice. That means it's overall exothermic. Now, some textbooks will write lattice energy as a positive value because they are understood to be big and they're understood to be negative. And I see merit in making it a positive value so that we can say a larger lattice energy and not think a larger negative number. I'll keep it as a negative number and just make sure that we identify. Now, why we need to revisit Coulomb's law is the idea of being able to conceptualize the lattice energy overall. Now, when we look at these Qs, these are charges. These are going to be our ions, our anion and our cation. R is the radius or the distance between the two ions. So what this says is that opposites attract. A +1 and a -1 over a specific distance will always give us a negative energy. A negative multiplied by a positive is going to be negative. And as they get closer and closer together, as that denominator decreases, then the energy gets even larger, negative. So the lattice is favorable because of Coulomb's law. Opposites attracting and getting closer and closer and closer together releases energy, negative exothermic. What does that mean for something like NaCl versus MgO? We already talked about these two and compared just their charges earlier. Which one would have a bigger lattice energy? Well, think about Coulomb's law. If lattice energy is directly related to those ions coming together, whichever ions would produce a larger value here, Q1 times Q2, that will be the largest energy. That 1 over 4 pi epsilon is a constant. So in Coulomb's law, what we really want to focus on is opposites attracting here. The larger the charges, so +2s, -2s, +3s, -3s, the larger the charges, the larger the lattice energy. Specifically, if we think about +1 multiplied by -1, that's a -1. If we think about +2 multiplied by -2, that's a -4. Magnesium oxide will have 4 times as large of a lattice energy than sodium chloride. Okay, as we are continuing on, what I want to go over next, I will wrap up with conductivity, and then we'll end with naming of ionic compounds. Now, this is what Lewis was talking about. If we just stick 2 probes into solid ionic compounds, yes, there was an energy exchange, but they are locked in a lattice structure. And so those 2 solids, those 2 ions being solid, don't allow the electrical conductivity that we see when they are actually in aqueous mixtures. That aqueous idea means dissolved in water. What that does, water is allowed to break up the lattice structure, and what we see are free-floating ions. And that breakup of the lattice structure is something very important that we'll discuss in a later unit, but it was predicted in Lewis structures. Ionic compounds, when they are solid, are locked in the lattice structure. When those ionic compounds are allowed to dissolve in water, the ions are allowed to break up and commingle with the water molecules, and therefore they can conduct electricity. Now we'll wrap up with a brief idea of naming specifically ionic compounds. What we want to be able to look at is there are 3 main categories of naming ionic compounds, and there's a 4th category with a different kind of ionic formula unit, which is called a hydrate. So let's just talk first about the main groups. Now, for these main groups, their charges are predictable based off of where they are on the periodic table. So something like aluminum plus oxygen, we know aluminum makes a +3 charge, oxygen makes a -2 charge. In order to figure out the formula unit, again, ionic compounds, formula units, what we do is we either say, is it a 1-to-1 ratio? Or should we do the charge swap? With this, what we are identifying are Lewis dot atoms. And we know aluminum will be ready to donate 3 electrons, but oxygen is only ready to accept 1 or 2. Now, how do we balance this so that we don't have electrons just floating around in the solution? That doesn't happen. I like the charge swap method rather than going all the way back to Lewis atoms. Al2O3. I'll tell you why this works though. If we have aluminum with 3 Lewis dots and we have oxygen with 2 available places, we can put 1, 2, let's draw another oxygen until we balance and we fill up everything. There's another one, but now this oxygen needs another spot. Okay. Well, now we need another oxygen, and we see the light at the end of the tunnel. Why the charge swap works is it's trying to balance, right? We physically have 2 aluminums. There's the 2. And we have 3 oxygens. There's the 3. Another way we could look at this is if we had 2 aluminums with a +3 charge and we had 3 oxygens with a -2 charge, that overall is a net 0 charge. That is what we always want to be able to see in an ionic compound. We should have a net 0 charge. So hopefully that solidifies the charge swap for you so that you will accept it as what it is. Now, potassium and fluorine. Potassium is a +1, fluorine is a -1. That's a 1-to-1 ratio, so I get to write that 1-to-1 ratio. Let's do one more before we get into the naming. Magnesium and sulfur. Magnesium is a +2 charge. Sulfur is a -2 charge. Again, a 1-to-1 ratio. Mgs. If you thought, let's do the charge swap, Mg2S2, remember, a formula unit is the smallest whole number ratio. So you can do that, but then just drop it down to its smallest whole number ratio. 2 to 2 becomes 1 to 1. Now, with naming, what we want to be able to do is take the cation as its element name, and the anion, we are going to change to the IDE ending. So aluminum and oxygen become aluminum oxygen becomes oxide. KF, potassium. Fluorine becomes fluoride. MgS, magnesium. Sulfur becomes sulfide. Excellent. Those are our main groups. Now we don't need to write anything with the charges for those main groups because they're understood. For any cation that is a transition metal, we run into a little problem. The problem that we run into is that there are multiple different types of ions, unpredictable charges. So which one are you talking about when you say iron oxide? Well, for a transition metal, when we have an unpredictable charge, we need to, in parentheses, right after that metal, put the Roman numerals of its charge. That 2 tells us iron is a +2 charge, oxygen is a main group, so he is predictable as that -2. Our formula unit is FeO. Now, there is such a thing as iron 3 oxide. Fe+3 and oxygen -2. Not a 1-to-1 ratio anymore, so the charge swap, Fe2O3. So anytime we have a transition metal or even a post-transition metal, things like lead or tin, we always need to follow the name with the Roman numeral. Other than that, they follow the typical main group elements. Now, you'll see that there are some older names. We don't need to use the older names. The new name with the Roman numerals is a new substitution for that. I do like looking at these because sometimes on old bottles that you can see in any of the antique stores in the orange circle, they sometimes have weird stuff that have their old school name. You never know where people get these bottles. And so some of the older names like chromic or ferrous or ferric will help us identify what charge was the transition metal taking. When Lauren was a lot younger and took general chemistry, we had to know these names. Yes, the newer name system was around. I'm not that old, but I had to memorize, which is not one of my favorite things, but I had to memorize some of these names. What we'll see is that a lot of the endings are OUS or IC, cobaltus, cobaltic, cuprous, cupric. The OUS is always the smaller charge. The IC is always the larger charge. The easiest one that I always remember was ferrous, because Ferrous Bueller had 2 friends, and ferrous is Fe+2. If you're too young to know that reference to Ferris Bueller's Day Off, I feel very old. You don't need to tell me if you don't understand that reference. That will be your homework. Watch Ferris Bueller's Day Off. All right, group number 3, polyatomic ions. Now, the polyatomic ions are very, very weird. I'll show you them and then we'll go over their naming. The polyatomic ions are a group of covalently bonded nonmetals. Some of them are metals. We see chromium in there, but a lot of these are covalently bonded, sharing electrons, but they're charged at the end of the day. They're very unique ions. Polyatomic, many atoms, and ions, they're all charged. A lot of them are anions. We do have a couple positively charged things. Specifically on this one is ammonium, NH4+1. There is another one, I'll just go ahead and write it right here, hydronium. Not often seen in this discussion of ionic bonds, but we'll see hydronium a little bit later. So I wanted to present it. It's H3O+1. Now with these polyatomics, these are set in stone. These you have to know. And I will have in class a list that I think are the most important, and wink, wink, wink. But you should know all of these for purposes of exams or purposes for homework especially. Now with the polyatomics, you utilize them as their own ion, whether it's an anion or a cation. I'll show you both. And when it comes to these polyatomics, things like NH4 plus 1 and chlorine minus 1, you get to do the same rules. 1-to-1 or the charge swap. These are 1-to-1. Now with the name for the cation, it's just the name of the polyatomic. Ammonium, and since chlorine is a main group, we put the IDE ending on it. Now, if we were to switch this up and say something like sodium and NO3 minus 1, which is our nitrate polyatomic, we still bring the formula unit together, same as before, 1-to-1 ratio. But now, instead of changing the ending on the anion, because the anion is a polyatomic, we just keep the name of the polyatomic. So don't ever change the name of a polyatomic in an ionic compound. We will see that we can change the name of a polyatomic when it is in an acid, but not for an ionic compound. All right, just to continue on, magnesium, nitrite. Notice for this one specifically, because we have to do the charge swap, and because the polyatomic gets a subscript, I have to use parentheses to identify the idea that that polyatomic is a unit. Do not just write this. This is bad. What is going on? Huh? Question? No. Put that parentheses around it to keep those polyatomics consistent. Now, I didn't need a parentheses for the previous example with nitrate because there was no subscript to put down there. So don't put parentheses if you don't need them, but if you need them, go ahead and put them on there. Namely, put them on there when the polyatomic has a subscript. Magnesium, nitrite. Notice that all of these are two words. You put a space in between them and you'll be good. All right, those polyatomics are important to note. Again, we'll discuss in class the important ones that I think are not only important for our exams, but future laboratory skills. Okay, one more thing that we're going to talk about before we end today is looking at our last ionic compound naming group, the hydrates. Hydrates are a special class of ionic compounds. It's an ionic compound that within the crystal lattice structure contains water. Now, what that means is that when we start looking at the actual compound itself, it looks a little bit longer for its formula unit. Some things to note: there's this dot. That's the hydrate dot. That raised dot is there to identify that we have incorporated with our calcium sulfate 5 H2O molecules. So we name the ionic compound the same as before. Whatever category it fit into, 1, 2, or 3, main group, transition elements, or polyatomic, plus we add a prefix plus the word hydrate. Now what that prefix can be is identifying 1 for mono, 2 is di, 3 tri, 4 tetra, 5 penta, 6 is hexa, 7 hepta, 8 octa, 9 nona, 10 deca. Now, we'll name CaSO4, calcium, main group element, no charge needed in a Roman numeral. Polyatomic sulfate, no change there in the ending because it's a polyatomic. Pentahydrate, one word. Let's do another one. We see again a main group cation, magnesium. We see a polyatomic. That's very common for these, not required, but common. Carbonate, trihydrate. We will practice with all of these namings of ionic compounds in class. The last group of naming that we want to discuss is covalent compounds. These are also called molecular compounds. To emphasize that idea again, molecules are things that share electrons. So with naming for these molecules, we see a very straightforward one way to name a covalent compound. Because we have the law of multiple proportions, which says things like this: atoms can bond in multiple different ratios to make different compounds. What we start to see is that carbons and hydrogens can form in a variety of different ways. Same thing with hydrogen and oxygen. Molecular compounds, molecules, things that share electrons, can share in a variety of ways. And so there isn't a formula unit, rather there is a molecular formula. It's an actual ratio of atoms. So when we look at a couple of different covalent compounds, when naming these covalent compounds, we are very fixed in our formula. We'll start with a prefix for the first element. That prefix will tell us how many of the first element we have, and then we'll have another prefix plus the second element, and that second element gets the IDE ending. So there's a similarity with covalent compounds versus ionic compounds. One thing to note is this prefix in the front gets to be dropped if it's mono. We'll see a couple of examples with that. Now again, our prefixes, just like we had up here, mono, di, tri, tetra, penta, hexa, hepta, octa, and nona, those are all our prefixes that we have. Now, let's just go ahead and start with C2H4, dicarbon, tetra, hydrogen becomes hydride. Now, there is a more common name for this. It's an organic chemistry molecule because it has carbons and hydrogens, but we won't be dealing with the naming system for organic carbons. We're going to follow this systematic naming for molecular compounds. Let's take CO2 for an example. 1 carbon and 2 oxygens. So the first element, it would have been monocarbon. We get to drop that mono. It's understood. Dioxide. CO, another example of the law of multiple proportions. Carbon monoxide. We can get even crazier things like P4O10, tetraphosphorus, dec oxide. So there you have it. When we're looking at all of the covalent or molecular compounds, a much more straightforward approach to naming because we have sharing of electrons, the law of multiple proportions is very prevalent. Okay, so we have discussed how to name compounds. We can write some formulas for them. And so now what would be useful is to be able to quantify the mass of that compound. We have a couple different things under our tool belt, but what we really want to discuss now is the idea of formula mass, also called a molar mass, and the mole. We briefly discussed what the mole is. We're going to investigate it a little bit more now as it relates to the molecules and the compounds that we just have built up in this chapter. So just as we've had a formula unit, which is the smallest whole number ratio of ions, that would be in an ionic bond. We can have a formula mass, which is going to be looked at as the average mass of a molecule based off of its formula. Why is this important? Well, when we're talking about something like sodium chloride, we know that sodium chloride is a ratio of sodium plus 1 and chlorine minus 1 built up in the lattice structure of sodium chloride, ionic compound. When we look at utilizing this in the lab, we don't have sodium element or chlorine element anymore. We have the ions and they are collectively together in the ionic compound sodium chloride. So when we're looking at utilizing our samples in the lab, the mole, remember, brought together the subatomic realm to the laboratory realm. And since we don't just look at elements, we also need to utilize that mole in compounds. So the formula mass of something like NaCl is going to be the sum of its elements. Particularly, there's one sodium, which is 22.990 grams per mole on the periodic table, plus one chlorine, which is 35.45 grams per mole. So they're additive. Together, they're 58.44 grams per mole sodium chloride. Why is that helpful? Because now we can go through the mole to get to how many atoms or how many ions. For example, a sample of NaCl has a mass of 17.2 grams. how many molecules or we can say formula units of NaCl are there in the sample. Just like we used before, mass can be converted to moles. Now, what we are going to use to convert to moles is our molar mass, our summed up, our additive formula mass. And then we can use Avogadro's number just like before. Notice how we can now change Avogadro's number to 6.022 times 10 to the 23rd formula units of NaCl per 1 mole of NaCl. So again, making sure that grams cancels with grams, moles cancels with moles, we're left with formula units of NaCl. We can punch those into our calculator. And what we really want to make sure, again, is we revisit the idea of significant figures. Again, a molar mass, a formula mass, just like a unit conversion, will always be infinite number of sig figs. So here, in our measured value, will be our 3 sig figs. 1.77 times 10 to the 23rd formula units of NaCl. That's going to be very important for us for either an ionic compound or a molecular compound. They're all going to be calculated the same way, but we can now interconvert between sodium chloride mass and all the way to sodium chloride formula units. Let's just see one more. If a sample of CO2 contains 6.11 times 10 to the 24 molecules of CO2, what is the mass of the sample? So again, in order to go from molecules to mass, we will need to be able to calculate a formula mass or a molecular mass for something like carbon dioxide. Just because it's a covalent compound does not mean it's any different than our molecular compound or our ionic compound that we just did. So looking at CO2, 1 carbon is 12.01 grams per mole. O2 would be 2 times 15.999 grams per mole. Add those up, and you're getting around 44.01 grams per mole for the molar mass of carbon dioxide. Now, when we set that up, the measured value that we are starting with is in molecules. So we would multiply it by 1 mole of CO2 over 6.022 times 10 to the 23rd molecules, and then multiply it by that molar mass. Making sure everything still cancels out, molecules with molecules, moles with moles, we're left with grams of CO2, 4.47 times 10 to the 2 grams of CO2. You could also put that in Non-scientific notation, 447 grams. Either one is appropriate. 3 sig figs though, because of our given measured value. So when we're looking at these calculations, now that we have built up our molecules and our compounds, we can do the same mole type calculations that we had done before. Okay. Now, when we are looking at the composition of compounds, a chemical formula indicates the relative quantities of each element in that compound. And that's extremely useful information. Scientists have tried to investigate unknown compounds and tried to find what their composition is, tried to find what their formulas were. So I want us to think way back, even just 35 years ago, there was a ton of research with ozone and the destruction of the ozone layer in our atmosphere. And one of the main components was a CFC, a chlorofluorocarbon. And the scientists, even back 35 years ago, did not know what those compounds look like or what their composition were. And so what we're going to talk about now is how scientists actually discover the composition of compounds. How are molecular formulas discovered? The scientists who worked on chlorofluorocarbons actually received the Nobel Prize for their discovery of the structures of CFCs that were making that hole in the ozone layer. A couple of them actually worked at the University of California, Irvine, not too far away, for some time as well. For our composition of compounds, one of the main ways to develop the idea of composition is a mass percent. And a mass percent is going to be calculated using the mass of an element divided by the total mass of the compound times 100%. So say, for instance, we wanted to take a typical very small CFC, carbon with 2 chlorines and 2 fluorines, and calculate the mass percent of chlorine, which is a big catalyst for the destruction of the ozone layer. So its percentage is one of the most important ones to figure out. We would say, okay, there are 2 chlorine elements. So there's that mass divided by the total. Again, the molar mass or the formula mass, which I usually abbreviate MM, would be 1 carbon, 2 chlorines, and 2 fluorines. And what we could calculate with that is 120.91 grams per mole. I'm not going to do units for this because the mass divided by mass would cancel out. So as long as your mass of the element is in grams per mole and your total mass is in grams per mole, you are good to go. 58.64%. Now again, sig figs are usually important, but they're not that important for this one since the periodic table that you're given has the masses of each element. Try to utilize that periodic table as best as you can, but no sig figs for this one, simply because they are variable based off of the periodic table that you're using. Now, what we could do with that mass percent is actually figure out a quick way of converting between grams of a compound to grams of an element, such as this. In 1.00 kilograms of CCl2F2, how many grams of chlorine are there? Now you could take this and go from kilograms to grams of CCl2F2, and then change it into moles, and then figure out a mole ratio, and then go to grams again. But because we have this mass percentage, we already have a conversion factor that says there are 58.64 grams of chlorine for every 100, remember it's a percentage, grams of CCl2F2. So mass percentage is actually a very useful way of being able to quickly convert from grams of one component to grams total or grams of another component in a given sample without really going through the mole. You are going through the mole, but you are doing it in a very underestimated way because you already have the mass percent. So when we're looking at this, conversion factors that you should know are this 100 or 1,000 grams to 1 kilogram, and that was in grams of whole compound, and now we'll just get grams of chlorine. I like doing things in scientific notation, but again, you don't have to. Either way, but 3 sig figs. What we note there is this idea that for every one compound, there are 2 moles of chlorine. There are 2 chlorine atoms in one CCl2F2 molecule. So what we could say is there are 2 moles of chlorine for every 1 mole of molecule. Very powerful tool. Okay. Now, in determining a chemical formula, that's if we have the chemical formula, we can utilize it. If we don't have the chemical formula, say we have component data like this, a sample of a nitrogen and oxygen compound has 24.5 grams of nitrogen and 70 grams, I'll say 70.0 for sig figs. We won't need the sig figs, but of oxygen. What is the empirical formula? What we have to remember is that our definition of the empirical formula. An empirical formula is going to be that smallest whole number ratio of atoms. Why it's important to be able to say empirical formula here is we can determine a molecular formula, but we're going to need a little bit more information. So let's look at this problem first and identify a couple of things. Now, we are given the individual masses, so we could calculate the moles. Remember, the moles are what bridges between our atoms and our mass. And so when we look at that smallest whole number ratio of atoms in the empirical formula, what we're really asking for is the smallest whole number ratio of moles. And so we can calculate the moles, and then find that smallest whole number ratio. So let's take 24.5 grams of nitrogen. Again, that is just a periodic table elemental nitrogen, not a molecule. So we are looking at using our molar masses or our atomic masses here. For nitrogen, we look on the periodic table, and that is 14.007 grams. So when we do that math, again, at the end of the day, we are going to be getting a whole number ratio. So sig figs don't really matter. Don't round too early. Yeah, I know there should be only 3 sig figs. I'll put a little note under there, but I'll carry out those sig figs a little bit so I don't have any rounding errors. Same thing for oxygen, 15.999 grams of oxygen. So when I'm doing this, what I have in mind is the idea that all of my formulas are going to be based off of the moles. Again, this is moles of nitrogen, moles of oxygen. Now, those don't look like whole numbers. And we don't want to round here either. We don't want to say 1.7 is 2 and 4.3 is 4. That's not what it is. So to find the smallest whole number ratio, what we actually want to do is imagine that these are subscripts. 4.375 under oxygen. I'll make nitrogen's a little smaller. 1.749. And we're going to divide by the smallest. By dividing by the smallest, what we can start to do is get that smallest whole number ratio. What we see with that is a nitrogen, that's a 1, and an oxygen that's a 2.5. Now we're closer. Again, we can't round, but we can say that a 1 to 2.5 ratio is really a 2 to 5 ratio. Multiply that by 2. 2.5 is really 2 1/2. To get rid of that half, I would multiply it by 2. But what I do to one side, I have to do to the other. So my empirical formula, N2O5. Smallest whole number ratio there. Now, that's awesome. That's great. Empirical formulas are helpful. The only way in order to actually get a molecular formula is to have another bit of information. So we can see by given mass data, just the mass data, we can calculate the empirical formula. By given mass percents, we can also find empirical formulas. A compound has 55.79% carbon, 7.04% hydrogen, and the rest oxygen. Determine the molecular formula if the molar mass is equal to 86.09 grams per mole. This is important information. The percentages will be able to tell us the empirical formula. We'll do that in a second. From that empirical formula, we can find its mass, the empirical mass. And then we'll compare the molar mass with the empirical masses, because the actual relationship between the molar mass and the empirical mass is going to tell us the relationship between the empirical formula and the molecular formula. So one thing to note is that mass percentages add up to 100. So we can look at the percentage for carbon and the percentage of hydrogen. If we subtract it from 100%, we'll get the percentage of oxygen. Again, since we're looking at formulas here, don't worry too much about sig figs. If you want to practice, that's great. But at the end of the day, you are getting a whole number ratio. From there, what we have with those three percentages is an actual mass number too. Change it to grams. Let's assume that we have 100 grams of compound. We get to assume whatever we want here. If we have percentages, we can assume 1 gram, 10 grams, 100 grams. So 55.7% carbon tells us that out of 100 grams of sample, 55.79 grams of it is carbon. We could convert that to our moles. So we're getting 4.65 moles carbon. Same for hydrogen. Make sure we're not using any diatomics here. This is not a diatomic type question. This isn't a reaction. This is just looking at the elements that are composed in this sample. 6.97 moles each. And we'll take that last one, 37.17 grams of oxygen. 1 mole of oxygen over 15.999 grams. And we get 2.32. So when we look at this again, we divide by the smallest, 2.32, 2.32, 2.32 to try and normalize. And we see C2H3O1. That is the empirical formula. The one could be understood. You don't need that one there. If you wanted to erase it, you could. Not wrong if you wrote it. Now the mass of that empirical formula, adding up 2 carbons, 3 hydrogens, and 1 oxygen, is 43.05 grams per mole. Now if we take the 2 masses and divide them, big one divided by small one, we see that there is an integer of 2. That integer is the relationship between the empirical and the molecular formula. So the molecular formula is going to be 2 times the empirical formula. C4H6O2. There you go. Now, another way of determining empirical formulas is through what we call combustion analysis. And for combustion analysis, it's very similar to what we've been dealing with, looking at the moles and trying to figure out the smallest whole number ratio for everything. But what a combustion analysis, why it looks slightly different, is because you have an unknown that you are reacting with oxygen gas to form carbon dioxide and water. Now, when you do this in the lab, you do it in a very different type of system. I have an image of that system later on that I'll show you. Normally, we don't do this in the lab simply because the system itself is not a closed system. You're not making a bomb, but in general, we don't often like to have explosions going on in our general chemistry lab. But when we do this, we get very, very important data. Namely, the data that we get are the masses of our products. So what's interesting about all of those masses that we know, the carbon in the product always comes from the unknown. The hydrogen in the product comes from the unknown. So usually what we have for this unknown is called a hydrocarbon. It's a hydrogen and carbon containing compound. So what we get to do with this is start to identify a couple of different things in this setup. So for instance, here would be the data question. A hydrocarbon is combusted in the lab to produce 1.83 grams CO2 and 0.901 grams H2O. Determine the empirical formula. We could also do the molecular formula if we had the molar mass. We'll just stick with the empirical formula. Now, a couple of extra steps here. We need to convert the moles of each, or convert the grams of each of these compounds to moles of the compound using their molar masses. However, we don't want the moles of just carbon dioxide. We want the moles of carbon. And for every molecule of CO2, there is one atom of carbon. So there is a 1-to-1 mole ratio. That is the value that we would like to have. So when we're looking at this, the one extra step in combustion analysis is the idea that we are using a molecular formula for carbon dioxide and water. But we still want to get down to the atomic level of moles, not of just CO2. We want to go further and get it for carbon itself. Same thing with water. There are 18.02 grams of H2O for every 1 mole of water, and there are 2 moles of hydrogen per 1 mole of H2O. That one's a tricky one to remember, so don't forget that 2 subscript in H2O tells you there are 2 hydrogens per 1 of water. Again, we take the smallest one, divide it. There's 1 carbon and 2.4 hydrogens. Now again, we can't convert that or round it. But what's really helpful is this chart right here. That 0.4 can't be rounded. These are just very, very helpful charts to remember. It's a multiple of 5. It's actually, if we think about 2.4, it's actually 12 over 5 in its fractional form. So what we would want to think about is carbon to the 1, H to the 12 over 5. If we multiply this by 5, we'll get the whole number ratio, C5H12. This chart is in your textbook. It's very, very helpful so that you can remember or start to recognize the fractional subscripts and know what to multiply by. Why we are multiplying by 5 is because it's a multiple of the fifth. 12 over 5 is 2.4. You can think about this is 1 over 5, 2 over 5, 1 over 4, 1 over 3, 1 over 2, 2 over 3, 3 over 4, 4 over 5. So what you're looking at there is just different variations of those fractions in decimal form, what we usually get out of our calculator. So be very aware, all of those denominators are what you are going to be multiplying by to get rid of the denominator. Excellent. So there is our combustion analysis. There are more complicated styles of questions. We're going to do those in class. However, what this basis allows us to do is start to see how we can manipulate the moles and manipulate masses and data from the lab in order to find empirical and molecular formulas. And I did say I would show you the combustion analysis setup. There's usually a lot of valves that go along with this. So oxygen, pure oxygen, is brought into a very sealed container so that it doesn't blow up. And that's where your sample goes, your hydrocarbon or your unknown. Now, when this is burned up, all the gas particles are funneled through different types of absorbers, a water absorber and a carbon dioxide absorber. Any leftover air that was also in this container in the furnace with the sample is then pushed out. The mass of H2O, the H2O absorber and the carbon dioxide absorber before and after the analysis is then taken so that you can see the difference in the weight. And the difference in the weight will be the amount of water or the amount of carbon dioxide. So that's a real life experiment with combustion analysis to develop or to investigate an unknown compound's empirical formula. Thank you all for joining.